Hello. Basically today I'm going to show the layout of a two-stage auto using open source tools and sky130 PDK. Basically here we have the layout. Before explaining the layout I will show the circuit. The circuit is a two-stage auto basically at a Miller op amp, also knowly called Miller op amp. Basically, the amplifier is composed of a constant transconductance cell. Basically, it's going to generate bias current that will be copied by this current mirror and will bias the first stage and the second stage. Here we have the most important part of the transconductance cell. Basically, this is what generates the current. This is as a ratio of 4 that is commonly used. This is a current sink and a voltage sink basically. Since the VDD is very high, this is used in order to reduce the V-drain source of these two transistors. And finally we have the current mirror composed of M5 and M1. Then the current is copied for the first stage with M6 and copied to the second stage through M12. Basically in the first stage we have a differential pair and an active load. Then we have a compensation network with a transistor CMOS working in the triad region and a beam capacitor. And then we have the input tube of the second stage, which is basically an NMOS. Starting with the current mirrors in the layout, we have here the current mirrors. Basically, the current mirrors of the transconductance cell are shown here, are these ones. Basically, they have a layout pattern which is actually very basic, is dummy A, B, B, A, dummy. This is also called interdigitation. And basically, the transistors that have their drain connected to the gate are put in the corners, and the transistors that don't have the gate connected to the drain are put in the middle. This is actually compensated for any usually errors by the X region. Then in the others that bias the first stage and the second stage are shown here. They have a very close pattern layout. Basically is A, B, B, A, dummy, and the dummy right here. This is done in order to compensate for the drop in the gate. So if there is a drop here in the gate, and here we'll have the larger drop of the current, basically we'll time out and make so the currents are more even. This is the voltage sink of the current transconductance mirror. Basically the constant transconductance basically is just a current mirror. This has the same layout pattern, but because they don't share the same terminals, we have to put dummies in as their connections. This will actually improve the wield and will actually improve proximity effects of the transistors, since it will force them all to have very equal characteristics during fabrication. Here we have I'm going to call this a current mirror, but this is not exactly a current mirror. This is a current mirror with a ratio of 4. Again, interdigitation. The transistors that have the drain connected to the gate are put in the corners, and the other transistors are put in the middle. In this case, we have two dummy types. We have these dummies and we have these dummies. Then we have the transistors that are connected to the resistor. The resistor, basically, to not put the resistor here and to put the resistors here, basically the current goes up here and then goes to the transistor. The transistor basically is done in a snake pattern. a snake pattern is like this. This is the current flow. Now it goes to here. These are basically dummies that I put. To the first stage, we have the M6, basically that is this current path, basically. There's this, and this, and basically goes to the differential pair. The differential pair uses a type of pattern called common centroid. Basically, it's a dummy, A, B, B, A, dummy, dummy, B, A, B, dummy. The gate connections are done in this type too. This is important to do. And the connections of the currents are done through here. Another important fact is this dummy, an annual is not actually connected to VDD, is connected to eBias, as seen here. This is done in order to cancel body effects. Then the current goes to the active load. Again, in the active load we have the same layout pattern that we use in the current mirrors. That is dummy A, B, B, A, dummy. So the transistors that have the drain connected to the gate are put in the corners, and the transistors that don't have are put in a middle. Then we have the connection to the bulk, the bulk connection to the ground, right here. Then we have the current path of the transistors that is not connected to the gate is the output of the first stage, right here. It will travel to the gate of the input transistor of the second stage, as we seen here, and will connect to the drain of the transistor in the triad region. Another important effect is that the gate of this transistor, of the triad transistor, is connected to this pad. This pad is the pad that is not connected to the gate of the PMOS, but is connected to the gate of the upper NMOS, as shown here. Continuing the layout, the output of the other terminal of this transistor is connected to the capacitors, right here. Then its other plate is connected to the output, Vout, that is connected basically to the drain of the input transistors that are biased by the current source, right here. This connection is shown right here. This is the connection, and this is Vout. Here I will show the DRC. Basically, there is no DRCs. The size is actually relatively small. Goes to okay. Put the calculator. 9. Wait, no, sorry. 29. So this is the approximate size of this amplifier. It's actually very small. Is not. This is extremely small. If we actually do the conversion to square millimeters. Right here we have the version in Magic. Wait. So again, we have no DRCs. I will do a small DRC update, but we have 0 DRCs. In here in Magic we can actually wait, for some reason it my bad, I locked the system. We can actually check the nets that are actually connected. This is a neat feature of Magic. We have the resistors right here, the NMOS, the NMOS, the NMOS, the differential pair, more NMOS and more NMOS. Okay, continuing, we have actually the net list of the circuit right here. It's actually a relatively large net list. This is the capacitors, the parasitic capacitors of the circuit. Actually, during the simulation of the circuit there were some problems. Basically it actually changed its specifications, so it doesn't actually comply with the specifications. It consumes more current than was actually initially thought of, in comparison with the spice to the original netlist. I don't understand why. And its phase margin actually reduced by a lot. So the GBW used to be close to 440 megahertz, and its phase margin used to be 60. Right now the GBW is at 83, and the phase margin is at 50. I did some actually changes to the layout, then tested the exported circuit, but it still has some problems. Here we have the consumption. The consumption increased by a lot. The offset is still manageable. The PCCR can have some improvements, but the larger problem has to do with the phase margin. It used to be 60, now it's 50. Again, this circuit is actually in my open source GitHub for anybody that wants to use. That's all.